Okay, have the example of a triple integral. It's just like a double integral, except you got three of them. So the inner integral, you integrate from -1 to 2 of x dx. So you don't need to look at anything else. We just rewrite the integral, but replace the integral from -1 to 2 of x dx with what that integral gives us. Antiderivative of x is x squared over 2, evaluated between -1 and 2. And that's going to then be 4/2 minus 1/2 or 3/2. So everything's written down, but this inner integral is worked out in 3 steps. And here we have it. So now we're going to want to do this integral, the y integral. So what's antiderivative of 3/2 dy? Well, it's 3/2 y. Straightforward. And I'm not going to write out all the steps. You know, it's going to be. We could have brought the 3/2 incidentally out of the integral at any point. Okay, I chose to leave it in there. But then we're going to have 3/2 times 3, which is 9/2, minus 3/2 times 2, which is 6/2. Okay, turns out that's just 3/2. And that's just 3/2 c evaluated between 1 and 4. And the arithmetic is simple. You're going to get 12/2, which is 12/2 minus 1/2, which is 11/2. I'm sorry, 12/2 minus 3/2, which is 9/2. If I did that correctly. Okay, so the integration is straightforward enough. What's this mean? For this region, well, x goes from -1 to 2. And y goes from 2 to 3. And z goes from 1 to 4. How do we depict this? And what's this integral telling us? It's fairly easy to sketch this region. Let's just take the region in the xy plane, which is where we usually look, but no reason we couldn't look at the yz plane or the xz plane. So we're going to look at the xy plane. Here we have the interval from -1 to 2. So here's where x is -1, and here's where x is 2. So the region -1 less or equal to x less or equal to 2 in the xy plane is an infinite strip. Infinite strip parallel to the y-axis. In 3 dimensions, it's everything above and below that infinite strip. Y from 2 to 3, well, let's say here's 2. And here's 3. So the inequality 2 less or equal to y less or equal to 3 in the xy plane corresponds to this infinite strip between y equals 2 and y equals 3. In 3 dimensions, it would correspond to everything above and below that. Okay, between the planes y equals 2 and y equals 3. Everything between those 2 planes. Well, looking just in the xy plane, I'll make a large solid line. My chalk will write, I'll make a for each of the boundaries, and of course, this gives us the rectangle out here in the XY plane. We want now Z goes from 1 to 4. And here's where X is -1. Let's just say that Z equals 1 here. This is not going to be a great job of doing this to scale, but 2, 3, 4 would be up here. Okay. Now, the region between Z equals 1 and Z equals 4, well, Z equals 1 in 3 dimensions describes a plane. Z equals 1 unit above the XY plane. Z equals 4 describes a plane 4 units above the XY. So, to get to the plane Z equals 1, starting down here, we would go 1 unit up. Okay. And here's where a region in the XY plane, or actually a three-dimensional region above this rectangle, infinite above and below, like an infinite prism, gets cut by the plane Z equals 1 along these lines. And these dotted lines. And then we go up to the plane where Z equals 4. And we got to go 4 units up to about here. And now we have these points 4 units above the XY plane. Oh, that's visible. This is visible. This is visible. And red colored is back in here. So use different colors to distinguish this region from the region down on the XY plane. So here's our region. Okay. It's floating above the XY plane, rectangular prism. Now, what you're integrating is you're integrating X. And that means that X goes from -1 to 2. Now, I was going to use, I didn't think it through, I was going to use a density. Let's say that you've got electric charge. Okay. So if X is electric charge, what's the meaning of the integral? Now, by charge density, charge per unit volume. You know that There are negative and positive charges, they attract each other. And of course, like charges repel each other. So somehow, maybe this is a block of material or some electronic device. Okay? And you have managed to get negative charge packed in between the, well, in the part of this region behind the axis plane, the small region back here, you have negative charge. It's denser on the back face of this prism and gets less dense. And by the time you get to the YZ plane, the charge is neutral. There's no charge for unit volume at that point. And then from there off to here, in other words, over 2/3 of the this a length, okay? 2/3 of this length, the charge is positive, and it goes all the way up to a charge of 2 units. Now you can see pretty clearly that if you want to look at the total charge, the negative charge from x equals -1 to 0, and the positive charge from x equals 0 to 1, which are now. Now they're going to add up a total of 0 charge, even though you got the charge separated, some of it back here, negative charge back here, positive charge here. The total charge between, let's say, here and here, the charge in 2/3 of this region is going to total 0. But then you got a positive charge beyond that. Well, what you do when you integrate is that would represent the total charge. And why does that represent the total charge? Well, excuse me. We can we do the integral with respect to x. You partition the x integral. So you've got a partition of the x integral. Okay, so you partition the x integral. Down here in the xy plane, you partition this x integral. So you've got these strips here down in the xy plane. Of course, you got everything above and below those strips. You can then partition the volume from here to here. So you partition this region into little rectangles. Now, for every one of those little rectangles, you've got a prism above that point. And you partition C. So what you end up with is a region enlarged somewhat. Would look like this. So if this corresponds to, let's say, this little rectangle here, then what's above this little rectangle is going to be one of these things. It's going to be kind of like here. Just like this. Well, when you do the integral with respect to Z, like partitioning this rectangle to a bunch of volume units. Okay, so you have a delta x here, delta y here, and here you have a delta z. So now you have a single volume increment. I don't know if it's me or the chalk, but the angle should be that position. There's the volume. Let's call this a delta xi, delta yj, delta zk. And the charge will be like an xi star, which is the density. Times delta xi, delta yj, delta zk. And now I realize that I might well be writing inside Zoom's famous watermark. Over here. We call it the law of natural cussedness. Natural resistance of the world to anything we try to do. Listen. Anyway. Okay, hopefully, if we were in the watermark, we'd escape it here. Okay, well, the point I'm trying to make then is, if we partition X, partition Y, and partition Z, our typical XY partition is going to give us a rectangle somewhere within this rectangle down here in the XY plane. And then we partition Z, and that chops up the rectangle within the region from Z equals 1 to Z equals 4, chops it up into little tiny rectangular solids, okay? You think of it as cubes, but maybe they're a little longer or a little shorter on one side than the other. So there's no convention to actually make these cubes, okay? But the essential thing is you partition it in such a way, and then you make all your delta x's and delta y's and delta z's the same kind of code too. That's something. Okay, and then you get the inlet. So we go from this charge to total charge, which we could generally write as a sum like I equals 1 to M, J equals 1 to M, K equals 1 to P, okay, of density times volume. This is density times volume. And then in the limit, without going into all the detail, this approaches the triple integral of x dx dy dz. And since x, well, your x partition went from x equals -1 to x equals 2. So -1 to 2 corresponds to this region. Okay. Y goes from 2 to 3. And z goes from 1 to 4. X goes from -1 to 2, y goes from 2 to 3, z goes from 1 to 4. And we just work this out. We see that the total charge is 9/2. So there's our total charge. And we can think of mass density, mass per unit. Okay, so it's like we have something that we've laid down with a 3D printer. And it uses some substance with very low density. Maybe the density of water, some solid with the density of water, those densities. And then we gradually increase the density as we go up. Now that would be density changes in Z, but that's okay. But whatever the density function is, go here, that's our end. And we get the total mass. Because we're always multiplying density by volume. How many coulombs per cubic meter times our volume, increment, or grams per cubic centimeter, or whatever. If it's charged, I think I just mixed my metaphor there. It's a coulombs per cubic meter, and then I went for grams per cubic centimeter. Coulombs per cubic meter, coulombs per centimeter, or nanocoulombs per cubic centimeter, cubic centimeter, not centimeter, or kilograms per cubic meter, or grams per cubic centimeter, or whatever. Nanograms per cubic micron, whatever. We multiply density by volume, we get how much stuff we got. And if that density is changing, then we have to use an integral. Okay, well, there's your total charge. What's the average charge density? Well, your average value of x is the integral divided by the volume. And the volume of this thing, 1 unit wide, 3 units long, 3 units high, volume dry. And of course, we could get the volume by just leaving x out of here. We just integrate the volume increment, then we get the total volume. So I'm actually going to do it that way. Okay, we integrate, I haven't written the limits and the interval of that, right, pretty small, but you understand, whatever the region, You do the triple integral of x with respect to x, y, and z, whether it's a rectangular region or a spherical region or whatever. You're going to get the total charge in this case. It's actually charge density, total mass, effective mass density, etc. Okay. When you integrate just the volume increment, you get the volume. Okay, well, in this case, if you integrate the volume increment, you're going to get nine, because of course that is the volume of this thing. It's a rectangular solid. We can easily calculate the volume, length times width times height, if you wish. And we get 1/2. Well, x changes linearly from -1 to 2 at every point. Okay, as we go from the back to the front, x goes from -1 to 2. What's the average between -1 and 2? Add -1 and 2 and divide by 2, right? You get 1/2. So the integral confirms that. Now, in this case, x being a linear function and all that stuff, it's real easy. If it was an x squared here, what would change in our integration? Notice it being x squared, right? That'd be x cubed over 3. So you'd have 7/3 instead of 3/2. Okay. Now to get your total charge, you'd be dividing (21/3) by 9. Okay, the integral will be 21/3. So you can work out the integral. It's real easy. Just about as easy as the original. Okay. Well, what do we see from this? First, we see that doing the integration is just like doing a double integration, except now I got 3 of them. So if you do double integration, you do the triple integration. That's no problem. Oh, hopefully. I mean, of course, if you have a really tricky integral, it could be a problem. So a simple integral for something that's within your realm, within your vocabulary of integration technique, it's not hard to do the integration. The region corresponding to our limits on the integral, the region of 3-dimensional space. So the integral can be interpreted as a density integral if you want to give you total mass, charge density, to give you total charge. Okay. Well, not all regions are rectangular. Okay, some regions are spherical, some regions are cylindrical, some regions are parabolic. You have to think of the quadrant surfaces. Okay. Setting up a triple integral in general requires some work. Okay. So let's just jump to I'm not going to do this. Okay. got the sphere, x squared plus y squared plus z squared equals 4. Well, that sphere is visualized and kind of sketch it. We can sketch. In the YZ plane, goes up to 2, down to -2. Over here, out to 2. Over here, to -2. Circle. Okay. In the XZ plane, it also goes out to 2. Let's just say the 2 is right here, and -2 is right here. So we're going to have something that's elliptical when you try to sketch it in 2 dimensions, 3 dimensions. Okay. Looks like this. And then up here, you'll have a similar but smaller circle. Then say the plane Z is 1. It'll look like maybe this. And then down here, it has something similar. So you can kind of start creating out a bunch of these to represent that. And you got something that, if you use your imagination, maybe looks like a sphere. Okay? Now we've kind of lost it, but in the XY plane, all the points of the sphere lie above and below this circle. So this is projection of the sphere into the XY plane. If you collapse things along the Z-axis, squash it down, you're going to have points inside this circle. Okay. And this circle is, of course, called the XY projection of the sphere the circle centered at the origin. Radius 2. Well, now we can say that we can describe this circle. Let's just kind of sketch it over here. So radius 2. In the XY plane. For a given value of x, as we saw the other day, either using the equation x squared plus y squared equals 4, this goes the circle. As an equation, x squared plus y squared equals 4. Well, we're going to partition. We've got a partition. We choose the partition. Here's an x. Our limits on y go from here to here. Okay, if this is x, then again we can do this geometrically. Did this picture the other day. Like Pythagorean theorem. Well, first of all, since this is a circle, this segment here goes from the center to the circle, as we said before. Length is 2. This side has a length that's actually the absolute value of x. X is negative. That's absolute value of x. And whether x is positive or negative, the Pythagorean theorem is going to have a square, so it really doesn't matter with this expression. Okay, so by the Pythagorean theorem, we have this. It's the equation of the circle, which of course is just a statement of Pythagorean theorem. Okay. But if we have the equation, we can always solve for y to see if y goes up to square root 4 minus x squared down to negative square root 4 minus x squared. So we can see that along this segment here, we have this. So now we can say that the circular region, well, x should go from -2 to 2. Okay. For a given x, y goes from negative square root of 4 minus x squared to square root of 4 minus x squared. And then what about z? Well, for a given x, y, let's say you have a point here. Okay, this is the point. X, y, 0. How far do we have to go to get up to the sphere? Or down to the sphere? So let's say here's for the segment above x, y, and the y plane. Intersects the circle above, intersects the circle of the sphere, intersects the sphere above, intersects the sphere below. Well, we can do something similar to what we did before. I'm going to draw a point here. This is a right triangle. Because this segment's in the xy plane and this segment's parallel to the z-axis, which means it's perpendicular to the xy plane. There's the triangle. This is very important too. You come to this fairly frequently, okay? So if I bring this triangle out here so I can label it and turn it so that we can actually see it. How long is this side? How far is it to the origin to the point xy? Well, the origin to the point xy, like the Pythagorean theorem, this side is the square root of x squared plus y squared. This side is 2. So this side has a length equal to the square root of 4 minus x squared minus y squared. Because it's going to be this squared minus this squared, right? Square this, you get x squared plus y squared. Square this, you get 4. 4 minus the quantity x squared plus y squared, 4 minus x squared minus y squared. And that's how far you got to go. In this case, you get down to the sphere. And you have to go the same distance to get up to the sphere. So now we conclude that the lowest you could go is negative square root of 4 minus x squared minus y squared. Next, that word. We have zoomed in here. Okay. I need to get used to this camera. Okay. Now again, watching the video, we sketched the sphere. Okay, we've done this before. We know that if you squash the sphere down, you get a circle of radius 2, which is like this. And what we did here is what we know. Okay, what we've already done, at least. So now we're trying to describe this sphere. Every point on the sphere lies above or below a point in the xy plane within the circle. And a point within the circle, well, the points within the circle could have an x-coordinate anywhere from -2 to 2. But once you know the x-coordinate, that limits how far you go in the y direction. Once you know x, you only go up to and down to the points on the circle. And the Pythagorean theorem, right there is the inequality that describes what y can do. And then we want to determine what z is. And I use this picture that we could see, but here's a point x, y, z, right? A point in the xy plane within this circle or this circle, okay? And how far do we have to go to get up or down to the sphere? Well, if this point is on the sphere, then it's 2 units from the origin. So this side for this triangle will be 2. This is the point xy from point 0, 0 to the point xy. Distance is square root of x squared plus y squared. So this triangle has a side equals square root of x squared plus y squared, a side of 2. And this is a right angle, a right triangle, a right angle here, because this side is right here in the xy plane, and this side is vertical, parallel to the z-axis, which is perpendicular to the xy plane. So you have a right triangle, so the Pythagorean theorem tells you how far you got to go to get down to the sphere. So we can go down as low as negative square root of 4 minus x squared minus y squared. Then we go up an equal distance to get the sphere in the upward direction. Okay. So now what's the volume of the sphere? We go from this description and understand that if we partition the x's, you want to think this through. You don't necessarily want to write out all the partitioning every time you do it in. It might be pretty tedious, but you got to keep reminding yourself of what you're doing. Partition this circle into vertical strips. And that would be like partition it into strips here. And then you partition each strip. So you get little rectangles. So you partition each strip down here, and that's going to give you a little rectangle. And then a typical rectangle, let's just say this is without wire rectangle. Typical rectangle will be a short plane then. Will contain a sample point. And if you sketch the rectangular prism, defined by this sample point, you can partition it. But each partition has a dimension delta x by delta y by delta z. And then you write your sum. You partition the interval from x equals -2 to 2. Right there you partition it to the vertical strips. You then, for each of these strips, you partition the y values from negative square root of 4 minus x squared to square root of 4 minus x squared. That gives you little rectangles, and for each little rectangle, you partition z from negative 4 minus x squared minus y squared to 4 minus x squared, 4 minus x squared minus y squared, and you get then triple integral Now you've got to be careful. You want to have x being the outer integral, and then y being x. And then this last one, and it's going to kind of crowded here. Okay. And this first integral will be with respect to z, because z goes from this to this. And then with respect to y, because for given z, y goes from here to here, okay? And then with respect to x, because x goes from -2 to 2. When you do the integral, when you integrate with respect to z, the z is going to get replaced by this and this. So it's not going to have any more z's in it, which is why you want z to be the innermost integral, because everything here is done in terms of x and y. Okay. Okay, so now you will dispense with z. When you integrate from here to here, you're going to replace y with this and this. So you're not going to have any y's left. So when you get down to the end, all you got left is x's. Okay? And what happens with y here? That's really bad with y. Sure, it'll be too hot. You know what it means. Okay? This y, when substituted in for z, becomes part of what we're integrating when we integrate with respect to y. So again, it's going to be substituted. We're going to substitute this for all our y's. We just get x's, and then our last integral will just have x's. Okay. Get fairly complicated, get fairly challenging, but yeah, lots of examples go by. So this is totally feasible. If we have a density function, a mass density function, we have the same limits in there, but I don't have room to write them in. Let's say our density function is some function of x, y, and z. It could be any function in this equation. So we just insert this because in any one of these increments, the delta x, delta y, delta z volume is going to be multiplied by the density at the sample point. Okay. So that's going to get us the mass of the small increment. And our sum, then taken to the limit, is what gives us this. So when you're thinking about what an integral means, think about what happens in a partition, what happens to one increment of that partition, one little volume increment. If you know what happens to one little volume increment, and you can describe the region with inequalities, then you know what goes inside the integral. It's whatever happens in that increment. If it's density, then it's density. If it's mass, you integrate. If you're integrating get mass, then you integrate the density times the volume. And the limits in the integral are just dictated by these inequalities. So if you develop these inequalities, you've got the integral. Then again, the task is to perform the integration. And hopefully integration techniques up to that. Some of the integrals can get pretty hairy. this one gets fairly hairy. You got to use trig substitutions. You got to use a lot of trig substitutions. Okay. Well, one more comment I'll make. If you're trying to integrate over the sphere, you know that polar coordinates are great for integrating over circles. The circle described in XY coordinates is like this, right? Okay. In polar coordinates, you just say r is less than or equal to 2. Okay, so just a side note here, but this is very relevant to what's coming up, because next thing we're getting into next week is spherical and cylindrical. So we have rectangular polar coordinates in 2 dimensions. We kind of extend that idea to get cylindrical coordinates. Cylindrical coordinates is just, instead of x and y, we just use r and theta like we do. And then we just use z. Okay? So r theta tells us where we are on the xy plane, then z tells us where we are above or below that. Or we do spherical coordinates, which I'm not going to try to describe right now. But just like this comment, that's much simpler. And of course, theta goes from 0 to 2 pi. There's no theta in the r limit, and there's no r in the theta limit. So this is analogous to what we did here. It was very easy to integrate because we didn't have any x's or y's or z's in any of these limits. They were just fixed. And of course, when that's the case in rectangular coordinates, what we get is some kind of a rectangular prism, rectangular solid. In polar coordinates, what we get if we don't have any of these is either a circle or a sector of a circle. If theta went from 0 to pi over 2, you don't have a corner of the circle. 0 to pi over 2 just gives you this much. Okay. Well, that's a little prelude. You want to be sure you understand that real well before we go into the three-dimensional stuff with the cylindrical and spherical coordinates. Right. Problems. Okay. So there we have it. Again, the most important thing, I'll repeat it once more, is describe the region in terms of inequalities, and you've got your limits in the integral. Bottom line. And think about what happens in one small increment. And that tells you what goes inside your integral. And that's really what it boils down to. Then, again, of course, it comes down to integration technique, which can be challenging. Probably want to review integration technique. Trig substitutions, integration by parts, and do all that. Okay, I'm glad this was recording. Sometimes I think it is and it isn't.